All right, today, everybody, we're going to be talking about making predictions. This is TEKS number 7.6C. Making predictions would be something that is directly related with experimental and theoretical probability, more so experimental probability. And it talks about how we look at the probability of an occurrence and how that is affected or how that affects the number of trials over time. Okay. Next, we're going to be looking at our schedule. Remember that we're going to be discussing simple probability and making predictions for the first two live lessons this week. And remember that all lessons for the summer bridge must be completed by June 30th. Now, this recording is meant to be applied specifically to making predictions. Don't if you're not in the summer bridge class, of course, the information is still going to be valid, but this was recorded during a summer bridge session. All right, remember our vocabulary is going to be dealing with sample and population. Remember that a total number of possible outcomes is what we're going to be talking about when we are thinking about the probability of something occurring. Proportion is directly related to making predictions as well because it's a statement of equality between two different ratios. Okay. Now, the number of occurrences over time can be put into ratio form. And remember, ratio is just a fancy way of saying a fraction. Probability, of course, is going to be the likelihood of something happening or something being specifically the case. Experimental probability, the probability of an event determined by carrying out a simulation or experiment. And then, of course, theoretical probability, the expected probability of an event occurring. So remember, the difference between theoretical is what could happen, and experimental probability deals with what did happen when something was tested, hence that root experiment, okay? All right, so we're going to look at our first example. In our first example, we see that a six-sided number cube is rolled. The probability of rolling a 3, of course, is going to be 1/6 because each of the sides of a six-sided number cube have an equal likelihood of being rolled in theory, okay? So that's why we have a 1/6 probability. This is the number of favorable outcomes. In this case, rolling a 3, okay? It's supposed to be a U, okay? Over the total number of possible outcomes. So I'm gonna erase that and do the initials here. That's favorable outcomes over possible outcomes, okay? So 1 out of 6. One occurrence being rolling the number 3 over the total possible outcomes, which is 6. So what I want to do is I want to use this probability to determine the likelihood of something occurring over time. So if I were to roll that number cube 30 times, how many times do I expect the number 3 to come up if I know that the theoretical probability is going to be 1/6? So what I would do is I would multiply 1/6 times, and remember the symbol will mean times, okay? 30 occurrences. And remember, I made those into two different ratios. This is a ratio. This is also a ratio, okay? And I'm going to erase that line, okay? So when I multiply these out, that is 1/6 times 30. And remember, I can cross simplify these to make them a little bit easier. The greatest common factor between 6 and 30, of course, is going to be 6. I can divide 6 by 6, giving me 1. 30 divided by 6, giving me 5. And so when I multiply across, multiply this way. So 1 times 5 gives me 5. 1 times 1 gives me 1. So I would estimate over the course of 30 rolls, being that I know that the probability of rolling a 3 is 1/6, multiplying 1/6 by 30, that would give me 5 occurrences. So for each of those numbers on the number cube, I'm expecting each of them, because they have an equal probability, to be 5, okay? So the probability of rolling a 3 over 30 times is 5 times, okay? Next, about 10% of the population is estimated to be left-handed. And I added that word in, and you'll see why in just a moment. Use this statistic to answer the questions below. So has every person in the world been polled, or do we know what hand each person in the entire world writes with? No, we don't. Okay. But we estimate that that's about a 10% likelihood. Okay. Or the probability is about 10%. Now, if you remember, a probability can be expressed as a percentage. So 10%, I'm going to erase that because that didn't look like a 10%. So 10%. Remember, it can be expressed as 0.10 or 1 out of 10. Okay, they all mean the exact same thing. So if I know that the probability can be expressed as 1/10, remember, I'm going to take my my theoretical probability, which is 1/10 or 10%, multiply that by 20. That's the number of people that I'm estimating in this class. So let's back up just a little bit, okay? So in a classroom of 20 people, about how many do you expect to be left-handed? So the word expect is going to be key here because that is dealing with the theoretical probability. It's not something that we've actually estimated. So we walk into a room, there are 20 students. If we know that overall it's estimated that about 10% or 1/10 of people are left-handed, about how many people do we expect? So we're going to do the exact same thing. If I were to multiply this across, this becomes 20/10. A little trick that I know to simplify, if there are ending zeros, I can cross through the number of zeros that I have. As long as there is a matching zero in the numerator and the denominator, I can go ahead and simplify it that way. So once I do that, that leaves me with 2/1 or just 2. So of those 20 people, think about what that means. 2 is 10% of 20. So we estimate that about 2 people in that room will be left-handed. Okay, let's look at the exact same stat or statistic. If we know that there are about 1,000 people in the school, how many do we expect to be left-handed? That is 1 out of 10. I'm going to again multiply that by 1,000. When I multiply this 1,000/10, okay? Remember, I can match up ending zeros. So in this case, I only have one pair of matching zeros. So that's 1 here. I can't cross through these other 2 here at the top because of the fact that there's not an ending zero in the denominator to match that with. So this becomes now 100/1 or just 100. So without actually taking an actual poll of everybody in the school, we expect about 100 people to be left-handed in the school using 1/10 as our stat. Now, are these numbers exactly how many people will be left-handed? No. Okay. This is just a prediction because of the fact that that is an estimate. So because something is theoretical, 10% of the population being 10% of the population being left-handed, we don't know that if we go into that school, there could be any number of occurrences. Maybe there's an overwhelming amount of people that have the genetic predisposition to be left-handed at that school. We don't know. Okay, so that doesn't mean that it's going to line up with what actually occurs in the real world. Next, we know that you have a batting average of 0.250. Okay, this means that the probability of your getting a hit is going to be 25%. If you have 520 attempts this season, about how many of those hits do we estimate or could we expect you to get? Okay, so we know that this and this mean the exact same thing. What does the ratio form or the fractional form of that probability look like? We know that it is 25/100, or if we simplify it, it's just 1/4. Okay? So we're going to look at that over the course of time. There's one of 2 ways that I could do this. I could actually multiply 520 times that decimal form, That was a 2. Or I could multiply 1/4 times 520. Okay. I could cross simplify, say, oh, what's the greatest number that I know right off the bat that I could divide these two by? That's dividing both by 2. That becomes 260. There's more common factors here. I can divide it again by 2. That becomes 130. So 1 times 130 over 1 times 1. So remember what I'm doing is I'm multiplying 1 times 130, 1 times 1. Okay, so 1 times 130 is 130. 130 over the number 1 is going to be just 130. So we expect over the course of that season that we would have 130 hits if we attempt 520 times. Okay. Okay, now lastly, there won't be any calculations here, but lastly, what we're showing is that Juan is watching cars go by on the road. He counts 10 out of 100 cars that are silver. Okay, so this means that the experimental probability of seeing a silver car is going to be 1 out of 10 or 10%. Okay, that's in his experience just standing on the side of the road in that particular occurrence. Okay, statistics for the distribution of car colors in North America is shown. We see that these are the colors as estimated in America. If you notice here, it says that about 15% of cars in North America are estimated to be silver. So the information given in the table must be wrong. I'm sorry, which of these statements is true? So this is an answer choice, this is an answer choice, so on and so forth, okay? So let's think about this. What if Juan was standing on the side of the road and there was a factory that built cars nearby, okay? And this particular factory did all of the silver cars in one part of the country. Is it going to be accurate if he was counting cars that actually went by, okay? Or say, for instance, the factory that he was standing by didn't do a lot of silver cars, okay? And he just happened to see them whizzing by because he only saw 10% of the cars that passed by. 10% of the cars that passed by him were silver, okay? But we're estimating over time that the overall average is about 15%, okay? So let's think about all of that. And there could be any number of possibilities that occurred. So I'm going to erase these marks. Okay. All right. So which of these is true? The information given in the table must be wrong because it does not match his experimental probability of what he was seeing. If he observed more cars over time, his experimental probability would get closer to the percentage given in the table. He must have miscounted because it does not match the information given in the table. Or if he observed more cars over time, his experimental probability would get further away from the percentage given in the table. Let's think about this. The information given in the table must be wrong. Is that true? No, because they are showing what they think to be a very close estimate of the number of silver cars in the country. Okay. So that's not going to be true because that probably something that was probably something that was actually measured in some way. Sorry, wrong one. Okay. If he observed more cars over time, his experimental probability would get closer to the percentage given in the table. That's an interesting one. He must have miscounted because it does not match the information given in the table. That's not necessarily the case. Okay. We don't know where he was standing, the time in which he was standing, what the outside factors are. So that's probably not going to be the best answer, that he miscounted. Okay, because what if he had set up a videotape and he actually sat there and he counted them over time? If in fact he did get 10 out of 100 cars and that was accurate, again, this is not going to be the best answer because we can't control or know what the outside factors were. Okay, like in that factory example that I gave you a moment ago. If he observed more cars over time, his experimental probability would get further away. Okay. So let's see. We're down to these last two. So just a little bit of background. Remember, in our previous lessons, we've talked about how if you have a penny or a nickel and you keep flipping it and you're trying to get heads or tails, It could happen where if I were to do 3 trials, if I were to flip a coin 3 times, it can land on heads all 3 times. It could land on tails all 3 times. It can land on a combination of heads and tails. Remember, that was only a few trials, but the closer or the more I do, the closer it's going to get to the theoretical probability, because the theoretical probability of rolling either heads or tails is going to be 1/2. Okay, if I rolled it or if I flipped it 3 times and it landed on heads all 3 times, that's 100% probability of landing on heads experimentally. If you flip the coin, it landed on tails all 3 times. Okay, that's 100% that it's going to land on tails experimentally. What if it was 1 heads and 2 tails? The probability of it landing on heads is going to be 1/3 or 33%. Remember, you want to try over time. You want to realize, it should say, no, and know that over time it's going to be closer to that theoretical probability. So this at the bottom is probably not going to be the best answer, because remember, your experimental probability and your theoretical probability will tend to line up the more you do, not get further apart. So the best answer is going to be here, that over time, the experimental probability would get closer to the percentage here in the table. Okay. So you guys, that will conclude our lesson on making predictions today. Now, whether or not you are in one of my summer school classes, the Summer Bridge, regular class, again, this information is still good. You may come to me or pull me aside separately, ask me a question more about experimental probability or theoretical or making predictions in class or a tutorial time frame. That is it for today, and I will see you guys soon.